smart farming systems. I also said a few things about it in my introduction this morning. But what I want to show you today is sort of like a case study, like an example of how we can use all those tools, digital image-based systems, IoT systems, smart farming systems to optimize fertigation to crops. Okay, so we're just taking a small piece of it. Fertigation is one of the concepts. Now you probably heard of the term fertigation. It's like what? Adding fertilizer and water together and supplying it, right? That's fertigation. So we are trying to optimize that. But I wanted to not just give a sort of like a story about a specific case. I want to show you different things that the smart farming can do, what it is, and how it's generally done, what opportunities are there, what traits one can measure, and then we dive into the case study. Okay? So slowly it will go through. The way I do my presentations, I'll have a lot of pictures. It'll be very little content. I want to make sure that you understand that. You don't need to start writing things. If it gets into your mind, that's more than enough for me. Okay? And I'll try to speak slowly, but feel free if you don't understand something, we don't have to wait till the end. Raise your hand and say, I'm not following. I'll go back and I'll explain it one more time. Because if you don't follow a slide, then you will not follow several slides after that. So it's important that you understand. Okay? I just put a fancy picture here. This is just computer vision. You're taking a picture, you can see a picture of tomato, you can section it. You can just look at the plant and then you can extract some information. I'll talk more about that. So there are three topics. I'm going to talk about fertilizer management, why it is so important. And by the way, I forgot to mention, my area of research is in protected horticulture. I work in that area, controlled environment agriculture, what you call here protected horticulture. I work in greenhouses, indoor farms. Your head of the department said high tunnels, all those things are part of my area of work. So the research I'm going to show you today is more related to that. However, the principles I'm going to talk about, they are applicable everywhere. You can use the same principles in other crops too, with a little bit of modification. Okay. Definitely have to modify a little bit, but it is definitely can be easily transferred to field crops as well. Okay, so I'm going to talk about fertilizer management in protected horticulture, why it is so important. I'm going to talk about some smart sensors, what they do, how they work, what they can measure. I think is it some sort of an auto mode or what? That it moves automatically?
It got touched by your hand.
So you want to go back? Bhavesh?
Yeah, but I just want.
Just.
I think it's going on some timing. Somebody you change it? Okay. All right.
The remote
yeah,
sensors.
I think it was maybe I touched it. But then I'll show you a case study where all of these things are put together and where we optimize fertilizer management. So those are the three things. Do you mind please close the door completely? Close the door completely.
Close it.
All right. So a little bit about Purdue University. We are located in West Lafayette. West Lafayette is the name of the city, and it's the name of the state is Indiana. You can probably easily remember this, right? Sounds like India.
Yes.
Indiana.
Yes, sir.
And we're about 2.5 hours. I really appreciate. I really want to do 150% to my students, but I also want 150% from my students. Okay? If I don't see that, I lose interest. So please be aware of that. But let's focus, because this is for you, right? It's not for me.
Yes, sir.
So just a little bit introduction. We're about 2.5 hours from Chicago. Chicago is a big city. It's a little bit south of Chicago. It's Purdue University, 2.5 hours. We have about 12 colleges. Most popular ones are engineering and agriculture. College of Engineering, College of Ag. College of Science is also very big, but there are also many other colleges. About 40 to 45,000 undergraduate students. We have about close to 3,000 graduate students. Graduate means postgraduates, masters and PhD put together. We have about 2,500 faculty and some other 2,000 plus professional staff. That's Purdue. Okay. We are ranked 88th globally, and we are 8th among US public universities. But in terms of specific colleges, College of Engineering is very highly ranked, like it's top 2 or 3 in the country. College of Ag is also 6 or 7 in the country, big. And this is horticulture, and these are our undergraduate students. So we have a mixed group of students from all over the world. But you see more of a diversified group when you look at the graduate students pool. They are almost 85% from all over the countries, very few actually from the United States. Okay. Very diversified university. So let's start with the fertilizer. You see this picture, I actually took this picture myself in a greenhouse. The grower had a problem. When I say grower, these are like farmers, but in greenhouses we call them growers. So the grower had a problem, he called me. I also have a lot of extension under my belt, so I tried to help them. And I went there and he showed me, and this is just a tiny picture. He has almost some 100,000 plants like that. They're all nutrient deficient, very classic nitrogen deficiency. The lower leaves are turning yellow. That's a nitrogen deficiency.
Yes, sir.
Plants. Okay. And he said, what's going on? And then we figured out that he had a fertigation system that was meant for both seedlings as well as mature plants. And he didn't have any specific fertigation system for this. And so he was trying to modulate nutrient supply to mature plants, but in doing so, he made big blunders with the smaller plants. But the problem I'm trying to emphasize is by this time, he called me for a solution, but I don't have any solution now. The problem is already there. Okay, maybe the next leaves that may come, he can take care of, but the damage is already done. He has committed to some landscaping groups. They have to come and they have to take the seedlings, and they don't have seedlings, so they're not going to come next year. They lose, market. It's a big deal for them. So in greenhouses, it is so important. Even today, so many things are there, but one of the fundamental issues we see in greenhouses is nutrient management, fertilizer management. It's very basic, but still the most important aspect of that. This is where the kind of technology sort of monitoring comes into play. But I wanted to show you a little bit more how fertigation is generally done. Most of them, oftentimes it's based on a timer. There is no information about whether plants need a fertilizer or not, how much should we add, nothing like that. They simply turn on fertigation at a specific time of the day, or maybe once every 2 days. That is common everywhere, simply because it's cheap. It's easy. You just buy a simple timer, and then you connect your pump to that. It will come on specifically at the intervals every day. After 24 hours, turn on the pump, fertilizer is applied to plants. So easy. It's one of the major issues. Nobody is properly paying attention to fertilizer needs from the plant side. But that's the majority. 85% of greenhouses use the timer based. There are some systems that use precision fertigation. Some little bit of formatting here, but I'm going to show an example of what precision fertigation is. In fact, your Vice Chancellor talked about it. The one that you have here, the fertigation system that you have here, is pretty much a precision fertigation system. And I have some examples from a greenhouse that I will show you in the next slide. Where we are going is with the smart fertigation. And this includes IoT and a lot of digital data. I wanted to emphasize one thing. You can apply fertilizer based on a timer. You can also apply fertilizer based on some sensors you place in soil. And when the sensor says there's less fertilizer in the soil, you can turn on fertigation. But the ultimate thing is, you should apply fertilizer based on plant demand, plant requirements. I'll give you an example. If it is next 1 week is going to be cloudy, cool temperatures, plants won't take a lot of nutrients because their growth is slow under those conditions. The amount of fertilizer you apply to plants depends on how they are growing. A fast-growing plant requires more concentrated fertilizer than a slow-growing plant. If you are applying on a timer, you're wasting fertilizer, maybe you're causing toxic effects. So what we are after with the smart fertigation is kind of measure whether plants need fertilizer or not, and then based on that apply fertilizer. How we do that, I'm going to show you that. We actually capture some images of the plants. From those images, we'll extract nutrient status of the plants. So we measure some indices that can actually tell us whether the plants need fertilizer or not. That is like the most advanced method of fertilizing plants. you will see a lot of people are trying to adopt this precision fertigation, where they put a sensor, and when the sensor says there is less fertilizer in the soil, immediately they apply fertilizer. But one more advanced, third generation of fertigation is based on actual plants, because that's what matters ultimately. I'll give you an example. You may apply fertilizer to the soil based on the sensor, but there is no guarantee that plants will take that fertilizer, because other factors like pH can influence nutrient activity, which is not under your control. So we really don't want to worry about all those things. We want to make sure that whether there is enough nutrients are there in the plant, at the tissue level, at the biochemical level, and then based on that apply fertilizer. That's smart fertigation. Okay? Just want to spend a little time so you understand these three things: a timer based, a sensor based, and finally something based on plant needs. Okay? So here is an example of sort of like a precision fertigation. So you can see a sensor, right there. It's a capacitance sensor. You can insert into the substrate or soil, and that will continuously give you the concentration of fertilizer or nutrients in the root zone. You can use controllers like this, electronic devices. You can simply program them. You can tell them that, whenever the nutrient status falls below a certain level, turn on the pumps and add fertilizer to plants. That's precision farming. And we've been using this almost 15, 20 years. In fact, when I did my PhD, this was actually speechless from my PhD days. So these are good. These systems are way advanced than those timer-based systems. The timer-based system doesn't even look at anything. Simply add fertilizer every day. Where here at least you are measuring something and then applying fertilizer. So it is definitely a big improvement. But still we don't know whether applied fertilizer is actually used in the plant. And that's where we want to go to the next system called the smart fertigation. So I kind of want to show it in a simpler way. This smart fertigation uses digital sensors. It works on IoT and also provides some decision support. 3 components. Okay? So what we use is, we also want to make sure that it's low cost. Remember I said that the technology should be adaptable. If it is not, then there's no value. It only gives you a paper. It makes your lab look nicer, but no farmer is going to use it. So we really want to go for the low cost technologies. We want to use images, and from plant images we want to know whether plants really need fertilizer or not. So for that we're going to use a 2D computer vision, top-down, 2-dimensional view. So look at this. This is a Raspberry Pi. Some of you may know Raspberry Pi. If you're not, it's a very cheap device. In India it is sold for 5,000 rupees. Okay. You can connect a nice tiny camera. It's an 8 megapixel camera to the Raspberry Pi. And you can use Python, OpenCV, to nicely code this Raspberry Pi, simple, to take pictures of the plants. From those pictures, you can extract some useful information, and the next slide I'm going to show you how that is done. But you can collect pictures. So we were interested in this type of system simply because it's cheap. For some 8,000, 9,000 rupees, converting things in Indian rupees, 8 to 9,000 rupees, you can buy this and this together. Maybe 10,000 rupees max, you can get them. Okay? And here is an example of something we put together. This basically is the same as this. It's about the size of a pen, and it's very cheap. For us, it's about $150 for 10, 12,000 rupees here. And then you can also connect it to a nice power bank, to power it, and then you can put it wherever you want. The nice thing about this is you can use this as an edge device, an edge sensor. So what is an edge sensor? An edge sensor is this is a cheap sensor. Let's say you have a big greenhouse. You can put these sensors at multiple locations. Because the more data you collect, the more powerful your analysis is going to be. Right? So you can place these edge sensors at multiple locations, and these sensors connect to internet. They connect to local Wi-Fi. They can connect to your phone's hotspot. Any internet is there, you can program them, and they'll automatically get connected. And so they not only collect images, inside these devices there's also some Python software that processes those images. Then, here is the interesting thing, they start sending the information to a central server. Server is nothing but another same sensor. It's just sitting in the middle. It is collecting the data from that corner, all corners. The server doesn't do any image processing, nothing like that. Its job is collect the data and make a decision. Okay, on an average, maybe there is little, less nutrition in this corner, but in general, the entire greenhouse is looking fine. So let me not apply fertilizer today. Or let's say if start seeing that all the sensors are saying that there is less fertilizer, except for this one, then it can make a decision. So the central server is just making a decision. It's collecting data from all these edge devices. And these edge devices are nothing but these. They not only capture image, they process image, they measure the nutrient status of the plants, and then send that information to the server on IoT. This is called IoT system, Internet of Things. These are all the different things on internet. Then, this server, central sensor, you can connect that to some electronic devices like pumps, lights, heating systems, cooling systems, whatever you want, spray systems, pesticide spray systems. You can ask these edge sensors to measure insects in different corners of the greenhouse, and when the insect threshold goes above, then the server can make a decision to turn on spraying systems. You understand this whole IoT? It's so easy, right? Unless once you know how to do that, the power comes from low cost. Power comes from more data that you're collecting rather than in one location or two locations. You're collecting from multiple locations. So this is smart farming. See, it's using digital sensors to measure, extract information from images. It is working on IoT, and it's also making a decision support, whether to or not to. That's a smart farm. Simplest term, that's what it is. You can expand this to field, you can expand it to orchard, you can do anything, but the concept is same. One more additional level that's happening is the server is now being trained by AI to make advanced decisions. For example, right now, there may be simple algorithms in there. There's a model there, measure from everywhere and kind of make a decision based on numbers. But AI, on the other hand, does something different. What AI does is it makes its own thinking. It uses, these sensors are saying that fertilizer is needed. However, I'm also getting information from the weather data that the next 1 week is going to be cold and cloudy. So I'm not going to apply fertilizer. See, it is making an advanced decision because of its training. It has got a model inside. The model tells that when environment, which is what your vice chancellor was telling you have to create the data now. The model tells the server that when the temperature is this much, when the light is this much, the growth is going to be this much, and therefore they don't need fertilizer. See, that model is what the AI trained server is going to use to even make advanced decisions. There are algorithm-based decisions, there are also AI-based decisions. But it's all happening right here. So I just want to give a very simple picture so you understand the whole smart farming and AI piece and everything. You can start building on that. Okay? That's why I spent a little time on this slide. I'm going to show you a system just like this in a greenhouse scale as a case study. Okay? But let's see what can you measure with these digital sensors. You can measure a lot of plant traits. So you can measure area of the plants, leaf area. You can measure chlorophyll levels. You can measure water status, canopy temperature. If the leaves are warmer, the stomata are closed, probably transpiration is less.
Yes.
So they may need water. Probably there is less water in the soil, that's why the transpiration is less. You can count seedlings, you can count flowers, you can count fruits. You can count, see like that you can see you know this flower? Anybody knows this flower? This is a floriculture. What is the name of that? Cut flowers. And anthuriums. Very expensive, they're very expensive. But the farmer is interested, I want to harvest anthuriums, I want to know how many are there in a unit area. You can just take a picture from that. You can get the number of flowers. You don't have to walk and count them. You can count fruits, you can count insects. All such things are very easily done. You can get the height and width of the plants if you're interested. You can measure like the areas there. You can see the seedlings. There's a big tray of hydroponic seedlings, lettuce seedlings. Just take a picture from that, you'll get the nicely segmented seedlings and you can count them. All these things can happen. And for example, let's say you have a huge greenhouse where you are growing 100,000 lettuce plants, 200,000 lettuce plants, and you sow them in these tiny seedlings. The number of seedlings is so important because that's the starting point of your production. If you have 10% less number of seedlings, your production is going to be 10% less because you don't have starting materials. You can count them manually, but if you have so many trays, hundreds and hundreds of trays, it's a lot of time and labor, but you can just take a picture with your phone actually and get that information like that. So there's a lot of powerful things you can get from this imaging, digital data. But now, not just collecting the data, put the data on IoT, and then also come up with some smart decisions. That's where the power becomes completely different. Earlier, people were only interested in, this is called phenotyping, basically. You're taking a picture and you're phenotyping plants, but you're not ending there. You're going 2 steps ahead. You're not collecting from one location, you're collecting multiple locations and transferring, communicating data, and then making wise decisions based on the data. Okay, just want to show you some of these things. Okay, so all this imaging, it doesn't happen like, it's not. There's a lot of processes that go inside. You can see here. You take a picture of 4 tomato seedlings, right? We enhance some specific channels in that image that we are interested in, and then afterwards we create a sort of like a black and white binary image. And then we take this binary image and we mask on this one, meaning what happens is all the white areas will remain in the final image and all the black areas will be gone. And then you ended up with what we call a segmented image. This is very, very important image processing. See the difference between this image and this image? What is the major difference? What else? What is missing? So you don't want to measure reflectance or anything from the soil. You want to measure plants. So the most important step is you segment out that background and only look at plants. Once you get to here, this point, you can measure the area, you can measure the number of pixels in that image. This may be a 8 million pixel frame, but you may only have 3.5 million pixels for the leaves. And from the pixel number, it's a piece of cake to get leaf area after that. Because each pixel has a tiny area. Okay. So as simple as that. You can also get reflectance, how much light is coming back from each pixel. And that light that is coming back has a meaning. Plants are supposed to absorb light in photosynthesis. But they are reflecting more, there is something going on, stress going on in the plants. It could be a lot of different things, but you can extract some useful information even from reflectance. It can be simple RGB. Somebody said they did RGB analysis. I talked to a gentleman, yeah, there you go. But you can also get some thermal reflectance. You can get reflectance from infrared bandwidth. All those have some value. But that happens with, it's basically Python OpenCV offers a wide range of tools that if you learn a little bit, collect some images, start playing with them. I'm an example. I am not a computer scientist. I'm not an engineer. I'm a plant physiologist, like most of you. Just I had interest. And so I started doing it myself many years back. And we were actually able to start with some hobby scale stuff to now more into some commercial scale stuff. It's an evolution with time. That's what I'm trying to say. As youngsters, you can learn so many other things. So just start learning few things that are out of your comfort zone. Just don't stay within your comfort zone. Just go a little bit out and start learning things and start implementing things. You might start seeing nice things. Okay? So yeah, the Python OpenCV is something that's a good starting point. And you got a lot of other software, C++, all of that. But start there. It's very simple. It just looks like English language. So you can start coding yourself. That said, one of the things that we were very interested from the beginning was this leaf area, canopy area, because it's directly tied with plant physiology. The bigger the leaf area, the more mass, generally, the more light interception, and because of that, more mass. That's a very important trait, especially in leafy greens and many other crops. Vegetative growth is directly related to leaf area. And this is something you can easily capture with image analysis. You can actually collect every day's data, or every hour of data, and even if you want every second data, you can do that. Simple programming. And from those images, you can measure how the plant size is increasing over time, as you can see here. As the days progress, when you start collecting data like that, now we are looking at growth rate of plants, but non-invasively. People used to cut the plants, weigh them to get the growth rates, relative growth rates, things like that. But here you can get relative leaf growth rate or relative growth rate of plants non-invasively. So we were very fascinated by this machine because it's directly tied to physiology. And we want to do a study, a case study, using the relative growth rate measurements, leaf growth measurements. I'll talk a little bit about this slide, but remember, all that smart fertigation that I'm going to show in the next few slides is based on that canopy area, that leaf area changes. They are directly tied to plant growth. They are directly tied to plant physiology. So we want to capture that. If plants are growing bigger, remember what I said, they need more fertilizer. If the plants are growing slower, they need less fertilizer. And how can you know whether they're growing faster or slower? Using canopy area, measuring every day, tracking it. So that's kind of the simple logic behind all of this, okay? But now, a case study, an example. We were at some point, and we're still doing a lot of research on organic production, crop production, in greenhouses. And one of the things we recognized very early is that organically grown crops. So here is a conventional fertilizer, synthetic fertilizer. And here is organic fertilizer. So this is the biomass, weight of the plants in grams on the y-axis, and different treatments that you'll see on the x-axis. Sorry again. But I'm going to explain them slowly. But what we started seeing was the synthetic fertilizer and the organic fertilizer contained nearly similar amounts of nutrients. Nitrogen, phosphorus, potassium, calcium, magnesium, sulfur, iron, manganese, boron. All of those things were carefully calculated. We got organic fertilizers, synthetic fertilizers. We carefully calculated different elements, prepared our own mix of organic fertilizer and synthetic fertilizer, and then we supplied them to the plants. So the plants are receiving similar quantities of different nutrients. One of them is coming through an organic farm, and the other one is coming through synthetic fertilizers. End of the day, I want you to remember a lot of topics are going on in this country about natural farming, organic farming. You can grow natural fertilizers, synthetic fertilizers, organic fertilizers. It's just the matrix that holds the nutrients that is different between organic and synthetic farming. Plants will only take inorganic elements. Remember this. They cannot consume organic farms. Plants won't take organic proteins. The nutrients are inorganic, end of the day. They are nitrates, nitrogen, phosphorus, potassium, calcium. The only difference in organic farming is those elements are embedded in a protein matrix. This protein matrix has to be broken by bacteria at certain temperatures, so the nutrients gets released into soil solution, then the plants will take. What you are supplying is an organic matrix. That's all. That's the only reason you call it as an organic fertilizer. Okay? Just kind of digress a little bit. But these two had same concentration, a similar concentration of most of the nutrients, and look at the yields. Nearly 25% reduction in leafy greens, lettuce yields. And we saw very early. So we had to do something to increase yields in the organic production. So we came up with some organic liquid fertilizers. So they are sold in big bottles, and they are just NPK, 3 nutrients. But they are already in more soluble form. So when you apply, you're kind of adding more nutrients, so the yields will go up. So we did see a yield increase. 10 ml gave, 20 ml gave very similar yield. So kind of 10 ml per liter of that liquid feed is okay. And we didn't see much of an improvement with 20 ml, so 10 ml was okay. But if you have to add this 10 ml every other day in production, it's going to cost a lot. Each bottle is very expensive, the liquid feed. So we don't want to simply apply like a timer system. Apply every day is like a timer, right? We can do a sensor-based system, but we thought of, okay, let's apply this liquid feed based on plant demand. It's smart way. So we use the canopy area as our trait of interest. When the canopy area is growing, then apply it. The idea was very simple. Add a little bit of liquid fertilizer. Wait, don't do anything. Start measuring canopy growth. After you apply liquid fertilizer, the canopy growth has to happen, right? You have added a little bit more nutrients. If the growth happens in the next 2, 3, 4 days, then apply a little bit. If the growth doesn't happen, Wait until the growth happens. When we do something like that, we are actually saving or reducing the wastage of the liquid feed. Because end of the day, when you apply liquid feed, what is the outcome you're looking for? You're looking for growth. If the growth is not happening, why do you want to apply it? And when you do that, you'll start saving the liquid feed. You only apply when plants need. When plants are growing, you apply it. Make sense to you all of you? When only plants are growing, you apply it. And for that, you need the digital sensor to measure growth. And you need to collect data from multiple points. And then you need to make a decision whether the plants have grown or not as expected. And then turn on the fertigation system attached to that liquid feed. So all of that kind of nicely plays into our model of IoT smart farming. And therefore we decided to, let's see what happens with the liquid feed. So that's kind of like the background. And this is how the system kind of looked like in the picture. So we had a manual system where we are applying that liquid feed, every day, like a timer. Every day apply some liquid feed. Okay, and they were also getting some water in this hydroponic system. But we had a digital sensor on top of that. It was measuring how these plants are growing in the manual treatment and sharing that information with another sensor. This is our sensor-based system. This is a smart fertigation system where we have everything similar except that we had a tank of liquid feed here. This liquid feed was only added to plants when that sensor said yes, it's time to apply. So what's going on here is, this is getting every day. You see that brown liquid, that's the liquid feed that we apply every day. And we're measuring the growth. And we're also measuring growth here. That information is being sent to this sensor. And this sensor is measuring how much bigger these plants are compared to these. If these plants appear 10% more in size, then that sensor triggered liquid feed application. If the difference is like 3, 4, 5% between these two, that's random. It was not doing anything. It was only applying when there was a difference in growth. How is that perceived? Growth is measured here in the manual treatment. Growth is also measured in the sensor treatment. The information is sent on the IoT remotely. This is calculating the growth and then making a decision. Okay, the growth for the plants under mine are 10% less than the growth of them. So I think it's time to add fertilizer. But this was just one system, but then we had multiple units, replicated study. And what we found was when we do something like that, well, notice here, there is manual treatment and sensor treatment. Plants are growing, their area is being maintained. You don't see much of a difference. However, the big difference came in terms of fertilizer use efficiency. We applied more fertilizer in the manual treatment for the same growth, and we apply less fertilizer in the sensor treatment for the same growth. So fertilizer use efficiency is growth or biomass divided by the total amount of fertilizer applied or fertilizer cost, whatever it is. That went up significantly. This is the advantage of smart farming. This is where we are actually able to reduce the fertilizer use, expensive fertilizer use, but we got a similar growth. We did not get more growth, okay? But we saved on fertilizer, and we got the similar growth. So the efficiency went up. So this is sort of like an example. We actually we got access. This paper got access recently last one. These are the type of things one can do. You can measure the counts of aphids. We're doing a project on insects, where we are measuring aphid counts because aphid threshold is very small. In some crops, it's only 4 or 5 aphid. In some, it's 10. The moment you get to the threshold, you start spraying something. But you don't want to spray if the aphids are below the threshold. Prophylactic, we don't want. We want to wait until we get to that threshold. In order to do that manually, you have to, lift the leaves, count them. It's labor in very, very laborious process. But then you can put some of the, the sensors I've shown you. There are some of even smaller ones that are even cheaper than that. And they can nicely take a picture of the undersurface of the plants. Tomatoes are, capsicum, what we call here, bell peppers, whatever you call them. You take pictures of the undersurface of the plants, and whenever the aphid count goes up, it just triggers sprays. That's one thing we're doing. We're working on many other indices. So there are a lot of possibilities. This is just an example. The big picture that I want you to take with you is that whole smart farming thing. Digital components. Then there is a component of IoT where you collect the data from multiple locations and get it all centralized in one location. There is a decision happening in one of the sensors, and that is connected to electronic devices and pumps and lightings and heating systems. And then made based on the decision from a lot of data, some operations are happening completely automatically. That is the power of smart. Okay. That's all I have. Maybe this is the last slide. Yeah. So I want to talk a little bit about this P. Letter P stands for Purdue, but it is, it's not complete. Right? They did not finish that. There is a good reason for that, but the way it is now explained is that you're all students. When you finish your degree, when the students at Purdue finish the degree, they're not complete. They got more after this. Okay, that's a symbol of this. Unfinished. Letter P sits in the middle of Purdue University. That's all I got. Thank you very much. And I'll open up for any questions you may have. I hope the concept is something clear to you. I want you to understand what that smartphone is. It's not a difficult thing. If you know the details, it's not that difficult. You really don't need a complicated AI laboratory to achieve it. In your home, you can do that. Try to turn on lights in your room based on outside light intensity. You can create a tiny sensor for that and you can play with that. Start from that level. You get really interested. That's all. Just the first step is important. Okay, we'll start.
Thank you.
Okay, any questions for me? I don't know how much time we have or what we need to do.